Welcome to Discrete Mathematics with Applications 2 at McMaster University. I'm Mehrnoush Haskarpur and we'll talk about finite automata and regular expressions in this video. In this series of videos, we start by talking about theory of computation, different models of computation and their power. And in particular, in this video, we will talk about one computational model, that is finite automata, and we'll discuss when it's deterministic, when it's non-deterministic, and what is the corresponding language to a finite automata. In the next videos, we will talk about other computational models that are push-down automata and Turing machine. So let's start with the theory of computation. It is the study of the foundations of computation. It evaluates questions such as, what does it mean for a function to be computable? What are the problems that we can define an algorithm for and implement that algorithm with a computational model? What are the mechanisms behind those computational models and how powerful they are compared to one another? What are the questions that they can answer to? And finally, how do we classify computable functions? So we can say that this theory evolves around three main topics: automata theory and formal languages, computability theory, and computational complexity theory. In this lecture, we will talk about the first one, which is automata theory and formal languages. We will get to know computational models, automata, and grammars, and get to know how they correspond to one another. So what is an automata? It is a computational model. It's an abstract machine that performs computations following a set of rules. We are interested in three categories of automata: finite automata with finite memory, push-down automata with finite memory and a stack, Turing machine with unlimited memory, and basically that's it, these three. There are variations and extensions of each of them, but we will only talk about their simplest and basic versions here. You can think of an automata as an abstract machine that we fed a word to, and we ask it to evaluate if that word has a certain structure or if it follows a certain set of constraints. In that case, we call that automaton an acceptor. In another example, we can give an automaton a word and ask it to translate it to some other word in a different language, to the same corresponding word in a different language. In that case, it is called a transducer, and it has a slightly different implementation. Okay, so now we have an idea of what are computational models. As we said, the first subdomain of computation theory is automata theory and formal languages. So it studies how the two things relate to one another. And that is why we study grammars and the languages that are produced by those grammars. A grammar is basically a set of rules for generating the expressions in a language, sentences acceptable in a language. It's typically made of a set of replacement rules that recursively produce a string acceptable for a language that contains only terminal symbols. So in a grammar, we have terminal symbols and we have non-terminal symbols. Terminal symbols are allowed to be in a word of the language, and non-terminal symbols should be replaced by other terminal or non-terminal symbols, and to finally produce a word that contains only terminal symbols. So, for example, an example of a grammar is something like this. So we have a set of rules, a couple of rules here. S is a non-terminal symbol, and A is a terminal symbol. And basically, this grammar produces sequences of A with arbitrary length. So if we have like an alphabet that contains only A, we want to produce any sequence of A. So A, anything, right? Any number of A's. So how we work with grammars is that we start by like a starting non-terminal symbol that's indicated by S here, and then iteratively we replace this S following the two rules that we have to create different words. So for example, here we can either replace S with A or with AS. If we replace it with A, we already have some string that contains only terminal symbols, and that is already an acceptable word in the language. as we have here. Otherwise, we can replace it by AS. So here we have a non-terminal symbol, so we need to move forward. It is still not a final word. We can either replace this S following the second rule, so it creates AA, which is another acceptable word in the language, or we replace it with the first rule, which gives us AAS. And then again here, or we can create different other words, or we can replace S with A and create the third acceptable word of the language. So this is more or less the idea of how formal grammars actually work. Another example is this one. So sometimes also empty word is acceptable in a language. So instead of only, this is very similar to the previous one, except that we also accept empty word, which is indicated by epsilon. So that means no symbol. This one means one symbol A. And so here we start by S. We can replace it with epsilon, or we can replace it by AS. And then here we can replace this S with epsilon, so it becomes A or AAS. And so the same thing that we've seen in the other one. Formal grammars have different sets of classes that are identified based on their expressiveness and power of computation, what kind of words they are capable of producing. So this set of classes looks sort of like a hierarchy. Some of them are capable of producing languages that are only a subset of languages that some other grammars can produce. Chomsky has introduced the ultimate classification of these grammars based on the type of languages they produce. And then there is a mapping between the languages that grammars produce and the languages produced by computational models that we've just seen, automata, finite state automata, Turing machine, and pushdown automata. So the languages that we can describe with no memory are called regular languages. So that is, or limited memory basically. Regular languages. These languages are accepted by finite state automata. So finite state automata. For example, assume a language that is made of, like the one that we've seen with grammars, so made out of words that are arbitrary sequences of A. And we show that by something like this. So a language that is produced by N being a variable that says any number of A's, basically, is an acceptable word for the language. And for this case, if we feed this word to a finite state automaton, it does not really need to count or keep count of the number of repetitions of S. The only thing it needs to do is to confirm that every symbol appearing in the word is A, right? So we do not really need to save A anywhere. We do not really need to keep count of number of repetitions of A. And this is an example of a language, a regular language, and it's the first class of grammars, the basic one. Then we have another set of grammars that are called context-free. So they're like a superclass for regular grammars. So context-free. These are acceptable by pushdown automata. So pushdown automata is basically like a finite state automata that has a stack as well. So it has finite memory, very limited memory to work with, and it has also an additional stack with respect to FSA. We will see later how it works. But basically, when we have a language that is made of all the words that basically contain the same number of A and B. So in this case, what PDA needs to do is to make sure that A and B are repeated with the same number of occurrences, right? So when it's reading A's, it needs to somewhere save N somewhere so that when it's reading B's, need to confirm that they are actually appearing, both of them are appearing N times. And so these are languages that require some kind of a stack to keep track of occurrence of different symbols. And these are implemented by PDAs. These are more kind of, they contain a bigger subset of languages, and they contain also regular languages as well. And then we have two other types of grammars that are accepted by Turing machines. We have context-sensitive and unrestricted grammars that are acceptable by Turing machines because they need infinite memory. The languages produced by these two are respectively called context-sensitive and recursively enumerable languages. So again, here, unrestricted grammars that are accepted by Turing machines, and they produce recursively enumerable languages. Okay, so going back to the slide, in the rest of this course, we will focus on 1, 2, and 4. So I didn't really draw context-sensitive grammars on the diagram. But as you've seen in the examples that I just talked about, so like AN or ANBN, in order to be able to talk about grammars and automata, we need to have some basic knowledge about how to work with the strings. And that is why we need to study string operations as well. So here we will see a few definitions of things that we've already seen or used before, like when I was giving examples of push-down automata, languages accepted by push-down automata or finite state automata, but also we've talked about these things when we were talking about predicate logic. But here we will see some formalized and precise definitions of those things. Okay, so first let's start with alphabet. So any string looks something like AB, BC, ABB. Any of them are strings, and they are all made of symbols. So in order to create strings, we need to have a predefined and finite set of symbols that we call alphabet, and we usually show by sigma. And a string is anything, so if we have sigma A, B, and C, and a string is anything that we can make by combining or by any permutation of A, B, and C. Then we can define a set we call sigma star, which contains any possible string that we can make from alphabet sigma. So A, B, and C themselves, but also their combinations like AB, BABC, anything with any length made from these three symbols. There is also empty word or empty string that we show by epsilon, and it's actually a word that does not have any symbols. That is always a word that we kind of consider as a subset of sigma star, which is every possibility on any given sigma alphabet. So it is always a subset of sigma star. And if the alphabet that we use, the sigma that we use, is actually epsilon, empty set, so we have no symbols here to make strings from, then the only string that we can make from that alphabet is epsilon. So it's like in sigma star we can put nothing except for epsilon. For any alphabet we can also define another set, which we show by sigma plus, which again is anything we can make from the alphabet, but things that actually have not length 0, so they have some symbols. So anything that we have in sigma star except for epsilon. Epsilon is not a member of this one. So they are basically the same set, and the only difference is epsilon. Any string is shown by a sequence of symbols, like these three examples that I have here. So you just write them as sequences of symbols, or you can just highlight them also or separate them from the word by quotations to make it more clear. But also a simple sequence of symbols are also acceptable. Then we have some operations defined on strings. The first one is concatenation. So if we have two strings, we can just put them together and make a more complex and longer string. So given the same alphabet that we had before in the previous slide, and a string could be AB, string 1 AB, string 2 BC A. Concatenation of the two looks like, so you just add the second one after the first one, AB BC A. But concatenation of 2 to 1 looks different, so that will be BCA AB. So they are two different words, two different strings. Each string has a length, which is the number of symbols it contains. If the string is empty, it doesn't have any symbols, so its length is 0. Otherwise, its length is the number of things that it contains. So, for example, length of S1 is 2, length of S2 is 3, and then the concatenation, the length of their concatenation would be the sum of length of the two, which is 5. Then we have repetition. So a few seconds ago, I used two examples for regular languages and context-free languages, AN and ANBN. So when we want to write down strings in which a symbol is repeated many times, instead of just writing it down, we write it as like this. So X is being repeated 2 times, 3 times, or n times. And when we use variables like n, it actually could define a pattern or a set of possible strings. So this one, for example, shows if for n greater or equal than 1, could show like the set of any arbitrary sequence of symbol A. Using this notation makes it easy to define strings because, well, it just looks shorter, but also you can more simply define relations or interrelations between the occurrences of different symbols. So for example, A and BN, this notation basically clearly shows that A and B need to be repeated the same number of times. We can also define more complicated patterns like A and B and C half of n, which says or highlights all the strings in which first all A's appear, then all B, and then all C appear, and then the number of A and B are the same. The number of C that come is half of A and B. So for n equal to 2, that would be A2, B2, C1, which is a string that looks like this. A, B, B, C. So this is how we can define long and more complicated strings. So the same operations that we defined on strings, we can more or less define on sets of strings as well. So we started by alphabet, and then we said how we can define strings from those alphabets, and now set of strings, right? And now we want to see what we can do with set of strings. So A and B are two sets of strings. Again, given the same alphabet we had before, A could be A, B, C, and B, C. And B could be like only A. Let's define B simple. So A and B are not only a set of characters anymore, they are a set of strings. So you can define typical string operations also on A and B, like union and intersection, and also complement. So complement basically means anything which we can define or is defined in sigma star, but not in A. And then we can also define concatenation on sets, which means every element of the concatenation basically is composed of 2 parts. The first part is an element of A, and the second part is an element of B. And then concatenation with empty set is empty. So for example, concatenation of A and B Well, no, let's add something to make it more like B and AC. So concatenation of A and B would be, you just pair every element of A to every element of B. So that would be AB would be, so the first element is A, B, C. You just put it together with anything in B, A, B, C, B. And then A, B, C, A, C. Then B, C, B, B, C, A, C. So these are the 4 elements of concatenation of A and B, which are different from concatenation of B to A, because the strings that are made from putting together first elements of B and then elements of A is different from AB. And then we have power, which we defined again on symbols and how they create strings. The same thing is true also for sets of strings. So basically any number of any power of I is a set of xy's where x is an element of AI and y is an element of A. So if we want to see an example on A, we can write it like this. So if we want to see what A2 is, it's basically concatenation of A and A. So ABC, 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 BC, and then the same for BC. Concatenation of BC with ABC and BC with BC. And then if we want A3, then we have to concat A with A2. And then we've defined sigma star and sigma plus. Here we have the same thing for sets. So every possible thing that we can create from concatenating A with itself several times in an iterative manner would go in A plus, and the same set excluding epsilon would go to A plus. I think here I said A plus, I meant A star. So I said earlier that finite state automaton or automaton in general are used as acceptors or transducers. For the first case, when we use them as acceptors, basically we give them a word, we give them a string, and they need to tell us if that word is acceptable or not under certain requirements or certain constraints, right? So an automata checks the pattern of the string, how it is made, and then tells us if it is actually part of a language or no. And so that is what we call decision problem. The automata decides if a word is part of a language or not. Now that we've seen operations or strings and how we actually define strings, how we perform certain operations on them, it's easier to approach decision problems and work on them. We will start talking about this in the next video.